Hello, my dear students. I am Aditya Chakraborty, lecturer in electrical engineering of Sri Ramakrishna Institute of Science and Technology. Today, I am going to discuss about the part 2 lecture of three-phase or polyphase. So today is a very important topic we have to discuss here, which is three-phase generation or how a three-phase is generated. In a three-phase system, there are three equal voltages or EMF of the same frequency having phase difference of 120 degrees. This voltage can be produced by a three-phase AC generator having three identical windings displaced apart from each other by 120 degrees of electrical. So if we rotate three-phase star connected winding, these windings the electrical angle between the windings are 120 degree, or the angular displacement between the windings are 120 degree apart, and if it cut the magnetic flux, then a three-phase voltage is generated, and the angular displacement between this voltage are also 120 degree. And we have to consider that the coils are identical. That means the coils which are formed the star connected three-phase winding are of same number of turns, or the resistance and inductive reactance of the coils are same, so it is identical in nature. When these windings are kept stationary and the magnetic field is rotated, as shown in the figure A, we can see it in the next slide, or when the windings kept stationary and the magnetic field is rotated, or vice versa, as shown in the figure B, an EMF is induced in each winding. The magnitude and frequency of these EMFs are same but are displaced apart from one another by an angle of 120 degree. So we can do both of these. This means that we can either rotate the magnetic flux or rotate the identical coils. So if the coil cut the magnetic flux, so according to Faraday's laws of electromagnetic induction, there is a voltage is induced, and here the three windings or three coils are apart from 120 degree each other, so the three numbers of voltage are induced in the three coil, and the electrical angle between these three voltages is also 120 degree. This is the three-phase generation. So here you can see the figure A and figure B. In figure A, the magnetic flux is mainly static and conductor is rotating in nature. So here you can see that this is the north pole and south pole, okay, and the conductor is rotating, so that is three conductors are at an angle of 120 degree from each other, okay. This is A dash, one conductor, that is B1 B2, sorry, A1 A2, B1 B2 and C1 C2. These three are three conductors. The angle between three conductors are 120 degree, so total that is the 360 degree, okay. And these are the identical coil, so voltage induced in each coil is also same. This is known as the phase voltage. And now you can see here, if the magnetic flux is rotating in nature, that is the rotor of an alternator, or you can see the it is a projecting pole type rotor or salient pole type rotor of an alternator, and the rotor is the field of the alternator, and when it is in rotating mode, the static conductor cuts the flax. These are the static conductors. This is the A1, A2, a coil, that is B1, B2, it's a coil, and one is C1 and C2. These three windings are connected, the stator windings, and the angular displacement between each winding is 120 degree. Okay, so that is the three-phase generation. And now the analysis. Consider three identical coils A1, A2, B1, B2 and C1, C2 as shown in the figure. In this figure, A1, B1 and C1 are the starting terminals. Here it is. This A1, B1 and C1 are the starting terminals, same as here. A1, B1 and C1 are the starting terminals. So you can see here the A1, that is A1, that is B1 and that is C1. So angle between this A1 and B1 is 120, A1 and C1 is 120, and C1 and B1 is also 120, same as here. Okay, whereas A2, B2 and C2 are the finished terminal of three coils. The phase difference of 120 degree has to be maintained between the start terminals A1, B1 and C1. Now let the three coils mounted on the same axis, and they are rotated by either keeping coil stationary and moving the magnetic field, or vice versa, in an anticlockwise direction at omega radian per second. Three EMFs are induced in the three coils respectively, and the electrical angle between three EMFs are 120 degree. Now the graphical representation of three phase. So here you can see the graphical representation. In figure C we can see that is the zero position, okay, or the initial position, that is the time period, and that is the EMF or E. So that is 0, that is minus 120, and that is plus 120. So from the 0, that is the EA1, A2, that is the first voltage or the voltage of the first coil. The angular distance between these coils are 120 degree, but the magnitude of the voltage induced in each coil are same, because these three coils are identical in nature. So same number of magnetic flux cut by the coil, so the voltage are also same, but the angle between these three coils are not same. So here you can see this is the peak value of the first coil voltage, okay, and this is the minus 120, that is 0, that is minus 120, or plus 240, and that is plus 120. So this is the peak value of the third coil, of the voltage of the third coil, and that is the peak value of the voltage of the second coil. So EA, EB and EC3 EMF are same, but these are apart from each other by 120 degree. This is the graphical representation of a three-phase system. Consider the figure C. The analysis of their magnitude and direction are given as follow. The EMF induced in the coil A1, A2 is 0 and is increasing in the positive direction as shown by the waveform in the above figure C. We can see here, or this picture, okay, this image. I have already discussed it. And it is represented as EA1A2. The coil B1 B2 is 120 degree electrical behind the A1 A2. The EMF induced in the coil is negative and is becoming maximum negative as shown by the wave EB1 B2. So here it is. That is 0 and that is minus 120, that is EB1 B2. And similarly, the coil C1 C2 is 120 degree electrical behind the coil B1 B2, or we can also say that C1 C2 is 240 degrees behind the coil A1 A2. The EMF induced in the coil is positive and decreasing as shown in the figure C, represented by the waveform EC1 C2. So that is the EC1 C2. Here it is, plus 240 degree or minus 120 degree. That is EC1 C2. So that is the analysis of the graphical representation of three phase. Now the phasor diagram of a three phase system. So if we analyze the three phase system by a vector diagram or phasor diagram, we can see that is these three are the peak value of the three voltages or the three induced EMF in the coils or the induced EMF in the each coils. Okay, one is EM C1 C2, one is EM A1 A2, one is EM B1 B2, and the angle between these coils are 120 degree. The EMF induced in three coils in three-phase circuit are of the same magnitude and frequency and are displaced by an angle of 120 degree from each other as shown in the figure, and you can see as shown in the phasor diagram. These EMFs of three-phase circuit can be expressed in the form of various equations given below. This is all about generation of three-phase power in three-phase circuit. Okay, so these equations are EA1A2 equals to EM sin omega t. EM is the maximum value of the EMF, okay, or peak value. Sin is the function of the sinusoidal wave, and omega is a radian. That means the 2 pi f or the cycle, and t is the time period. EB1 B2 equals to EM sin omega t minus 2 pi by 3, okay, or the angular displacement, that is 2 pi by 3 radian, that means minus 120 degree. So EM sin omega t minus 120 degree, and EC1 C2 equals to EM sin omega t minus 4 pi by 3. It is equals to minus 240 degree. That means EM equals to EC1 C2 equals to EM sin omega t minus 240 degree. So here we can see the magnitude of each of the EMF in each of the phase are same, but the angular displacement between these voltages are 120 degree. Okay, so that is the phasor diagram of three-phase generation. Thank you.